Hello, my name is Ertürk. My paper on the development of a 16-channel combined loop-dipole transceiver array for 7 Tesla body imaging was selected as one of the highlights of the Magnetic Resonance in Medicine issue of February 2017. Over the next few minutes, I'll share the details of our paper. Before diving into more technical aspects of this paper, I would like to mention a few related work. First of all, dipole antenna work by Alexander Reimakers and his colleagues at Utrecht University sparked a big interest on using antenna elements for high-field imaging applications. Fractionated dipole antenna work was also highlighted by MRM last year, I believe it was March issue, and I strongly recommend you checking it out if you are interested in high-field imaging and especially body imaging at 7 Tesla. In addition, combining loops and dipoles were proposed by Yiğitcan Eryaman when he was at MGH and also by Graham Wiggins from NYU. Through use of numerical modeling and simulations, Dr. Eryaman showed that by placing a dipole at the center of a loop element horizontally can cancel some of the local E-field electric fields produced by a local transmit loop coil in a spine array. In his approach, dipole antenna elements were placed orthogonal to the main magnetic field. Therefore, these elements did not contribute to excitation nor reception of B1 fields, but provided local SAR compared to the use of loop elements alone. And in his paper, he called this a dark modes approach. Also, both Dr. Eryaman and Dr. Wiggins showed initial numerical results of head coils utilizing both loop and dipole elements in the ISMRM of 2013. Here, with our work, we implemented a combined loop and dipole array for the first time for imaging the body at ultra-high field. Body imaging at 7 Tesla is extremely challenging due to shortened wavelengths causing constructive and destructive interferences resulting in excitation non-uniformity. Local transmit arrays are commonly used for imaging the body, but effective utilization of such arrays are usually limited by local power deposition concerns and local SAR limits. And for prostate investigation, centralized and deep location of this target makes it hard to achieve high B1 values. Using dipole antennas for body imaging applications are becoming increasingly popular due to increased field uniformity and improved field penetration of such elements. Fractionated dipole antenna design is especially important as it describes a recipe to tailor a dipole antenna element for improved transmit efficiency and SAR performance. A challenge with using dipole antenna elements is that a physical separation is generally necessary for acceptable coupling performance, and this might make it challenging to increase the element count without sacrificing coupling performance. To improve the performance of a dipole antenna array and also to utilize the capabilities of a 16-channel, fully independent transmit hardware, we decided to combine loop coils with fractionated dipole antenna elements and build a local transceiver array with 16 channels. On the right side of the slide, electric field vector direction and magnitude distributions of a dipole and a loop element along a coronal slice inside a phantom are shown. Electric field distribution of a dipole antenna element is symmetrical along its longitudinal axis, whereas a loop coil demonstrates an anti-symmetric electric field distribution along the same axis. So if we align a dipole and a loop along their center axes, then the mutual coupling between these two structures becomes zero, and therefore they are geometrically decoupled from each other. And so that by combining dipole and loop elements, we can place two resonance structures at the same location without worrying about their mutual coupling and increase the utilization of real estate. Here, B1 plus and SAR distributions of a combined loop dipole excitation with equal power and varying relative phases are animated. These fields are along an axial slice inside a uniform phantom. Figure at the bottom shows the peak local SAR and B1 plus transmit efficiency inside the annotated ROI. Depending on the relative phase between the loop and dipole, up to 26% higher transmit efficiency can be achieved. Due to slightly increased local SAR, about 21% of B1 plus SAR efficiency gain was realized when adjusting the relative phase of the loop and dipole. In addition to phase shimming, if we reduce the relative excitation power of the loop element compared to the dipole, peak local SER can be reduced by 30%, yielding an overall 35% increase in B1 plus star efficiency inside the uniform phantom compared to a single fractionated dipole antenna element. So everything works great in computer simulations, but how about building this coil? We chose not to alter the dipole antenna design and simply used fractionated dipole antenna design provided by Alexander Reimakers. We settled on a loop size of 8 by 18 cm squared. 18 cm length was chosen because it gave a similar field of view along the z dimension compared to the dipole. Width of the loop is limited to 8 cm to be able to place 8 loops around the body while providing enough spacing between neighboring elements to reduce coupling. Loop and dipole elements were printed on separate FR4 circuit boards, and low-loss Alton blocks were used to assemble each block. Loop and dipole elements were aligned along their central longitudinal axes, guided by the holes on the PCB boards and Alton blocks. An assembled loop dipole block is shown in the bottom right corner of the slide. To minimize cable interactions, we used first-order lattice balance at the feed point and secured the cables using cable ties. We repeated this process 7 more times and built a total number of 8 loop dipole blocks, and this means that we had a 16 independent transmit-receive channels. 2 flexible fabric housings, each housing holding 4 blocks, were custom tailored at a local shop. Neighboring loop dipole blocks had a center-to-center separation of about 12 cm. Flexible housing was instrumental in conforming the array around the body of different subjects and enabled us to maintain similar loading conditions between different subjects. By being able to maintain a similar loading condition between different subjects, we were able to build this coil as a fixed tune and match coil array. And this fixed tune and match nature of this array significantly reduced our subject preparation time prior to MRI studies. On the right, the array setup on a healthy volunteer prior to a prostate imaging study is shown. Final array was very lightweight and low profile, and all of our subjects were able to tolerate it really well without any reported discomfort due to the placement of this coil array. We evaluated the performance of the 16-channel loop dipole array using both simulations and experiments. Phase-only RF shimming was employed in this evaluation. B1 transmit efficiency, field uniformity, and signal-to-noise ratio metrics were measured inside the prostate, kidneys, and heart of the Duke model of the virtual family. Experiments were conducted on a Siemens Magnetom 7 Tesla scanner equipped with fully independent 16 1 kW power amplifiers. Again, phase-only RF shimming was done. B1 plus transmit efficiency and signal-to-noise ratio inside the prostate of 5 healthy volunteers were measured. Our 16-channel loop dipole antenna array was compared to 2 existing local transceiver body imaging arrays that are available at our institution. First array was a 16-channel microstripline array developed at the University of Minnesota. This array was the workhorse coil for all body imaging investigations in our institution until the development of the loop dipole array. And secondly, a 10-channel array consisting of 10 fractionated dipole antenna elements were used in comparison. We chose to use 10 dipole antenna elements instead of the original 8-element array because we were able to place 2 more antenna elements around the body of our subjects without sacrificing the decoupling performance. These comparisons were carried out both in numerical simulations and MRI experiments using the methods described in the previous slide. Simulated S-parameter metrics of the loop dipole array around the pelvis of numerical Duke model is shown. Interactions between dipoles and loops can be seen inside the upper right quadrant annotated in a red square. S21 between loops and dipoles on the same block were always less than -17 dB, and in most cases this interaction was even less than -25 dB. Coupling between neighboring loops and dipoles could reach up to -12 dB in this configuration. The highest amount of coupling occurred between neighboring loops, as can be seen in the lower right quadrant inside the yellow square. Coupling performance could be increased by Increasing the distance between neighboring elements or overlapping the loops would also reduce coupling between loop elements. However, overlapping the loops might increase the coupling between dipoles and neighboring loops, and here in this design, we relied on careful geometrical placement of the elements and also sufficient separation between neighboring loop and dipole plugs to reduce coupling to acceptable levels. This slide compares the transmit performance of the loop-dipole array against the 16-channel microstrip line array and the 10-channel fractionate dipole antenna array in simulations using Duke model and inside three different target anatomies. Phase-only RF shimming was done to generate this plot. Y-axis of the plot shows the transmit efficiency normalized to total array power. And of course, higher efficiency is better, and we want these points to be as high as possible on this plot. X-axis shows the coefficient of variation, which is a measure of field non-uniformity, and we want these values to be lower, closer to the y-axis. An ideal array with ideal excitation would have zero field non-uniformity and very high transmit efficiency, and would show up on the upper left corner of this plot. All arrays provided good field uniformity inside the prostate due to its small size. Field uniformity of the arrays containing dipole antenna elements were superior compared to the microstrip line array inside the heart and kidneys. In all of these simulations and in all of these phase shimming scenarios, 16-channel loop dipole array provided the highest transmit efficiency and best excitation performance. Signal-to-noise ratio of the microstrip line, dipole antenna, and combined loop dipole arrays along axial slices intersecting the prostate, kidneys, and heart are shown, and these target anatomies are annotated in the figures. Average signal-to-noise ratio inside the target anatomies are also listed below in this table for each array and each target location. The loop dipole array provides at least 20% SNR improvement compared to other two array configurations inside each target anatomy. Experimentally acquired transmit efficiency and signal-to-noise ratio of the arrays are listed in this figure. 5 healthy volunteers were scanned using each array, and average body mass index and pelvic AV dimensions of the subjects' populations were very similar for each array. Again, similar to numerical results as shown before, the combined loop dipole antenna array had on average 20% or higher transmit efficiency and signal-to-noise ratio improvements compared to other two arrays. 7 Tesla cardiac, renal, and prostate MRI of healthy volunteers acquired using the combined loop dipole antenna array are shown in this slide. Phase-only static RF shimming was used in the data acquisition in all of these images. We were able to achieve 0.5 mm in plane resolution in prostate images. Cardiac and renal MRI were void of significant B1 artifacts. However, more sophisticated B1 management methods, such as spoke pulses or parallel transmit pulse designs, would certainly improve the image quality even further. It is important to mention that dipole antenna elements produce more uniform excitation patterns compared to loop elements, and in applications that do not require very high peak B1 values, such as low field angle cardiac scans, loop elements can be turned off and field excitation can be provided using only 8 dipole elements, thus yielding a better field uniformity. On the other hand, we had to use all 16 channels to get sufficient B1 inside the prostate. In conclusion, we have developed a 7 Tesla body imaging array by combining loop and dipole elements and utilizing their complementary field characteristics. This novel array provided improved transmit and receive performance compared to a 16-channel microstrip line and a 10-channel fractionate dipole antenna array. Combining loops and dipoles with careful geometrical placement can offer very good decoupling performance while increasing the channel count and density. Channel count can be further increased by increasing the number of loop elements underneath each dipole. In our implementation, the use of a flexible fabric housing was instrumental in keeping the loading conditions very similar between different subjects. Maintaining a similar loading between different subjects enabled us to build this hardware as a fixed tune and match array and significantly improved our workflow at the 7 Tesla scanner. Now we can simply place the array on our subject and send them to the center of the board without worrying about mistuned or mismatched channels. Also, this lightweight and low-profile array was easily tolerated by all of our subjects with no discomfort reported. I would like to use this opportunity to advertise our ISMR abstract in the upcoming meeting. In this presentation, we will describe a 32-channel combined loop and dipole array. And finally, I would like to mention the funding sources that made this paper possible, and also I would like to thank my colleagues at the CMRR. Thank you for your attention, and please feel free to email me or Greg if you have any questions or comments. Thank you for listening.